I have a question for Molly. So thanks for the great talk. It definitely seems intuitive to me that you can't like have the best of all worlds, that you can't achieve low regret and try to test certain hypotheses and try, you can't have everything. But to your knowledge, is there any kind of like simple toy example where we have some impossibility theorem that would show us the extent, at least theoretically, it would show us the extent to which that cannot be done?
No, I don't have a really great toy example. I mean, what we did when we were running adaptive experiments was just run simulations with all of the different hypothetical parameter values that we thought about using, and then see if we could find some kind of like frontier where we could fix the best combination of them. And we just didn't find a really smooth, nice way to combine things to figure out like exactly what that trade-off is. No, I think that would be a great thing to have, and I would love to have that for illustration going forward. So if anyone has ideas about how to do that, I'd love to think about that. Thank you.
Thanks, Molly. So I just want to say a quick word about this and then also ask a question. So since this, I think it's a very confusing thing that the fact that algorithms that are optimal for regret are not optimal for inference.
Yes.
And the reason why is because they give up on any suboptimal arms.
Yes.
They give up on precision on those lower arms very quickly. In practice, this is often not as much of a problem as you would think because our confidence intervals are loose anyways. So in simulation, you'll always see this issue. However, in practice, confidence intervals tends to be a little bit inflated. A very quick fix, actually, to just be able to use regret minimizing algorithms to be optimal for, or to be, within a factor of 2 of doing the right thing for inference, is just inflate your confidence bounds. Multiply them all by like 1.5, and algorithms like UCB or Thompson sampling can work very effectively for inference. And so, and the reason why is, again, you're just getting the confidence bounds down. And so the guarantee of kind of these regret minimizing algorithms, right, is that they're learning the value of the best arm, but they're maybe not learning the identity of where that best arm is. But they're still going after that value very effectively. And even an algorithm just like uniformly pulling and then eliminating arms that you know are bad tends to be within a factor of 2 or a factor of 4 of the optimal regret. I think this is like just facts that about bandits people don't know, but get very confused about in this literature. I had a question though, just about your like experimental design. So when you run this, how big are your batches? Like the sample size you were showing us in those simulations was like 1,000. But oftentimes, if your gap is very small, you won't see an effect that quickly. So like, what kind of effect sizes were you going after? And how are you handling the fact that like, one of the issues I often have with these adaptive algorithms is there's a lot of non-stationarity. And that like, it's very dangerous. Even using something like top 2 Thompson sampling is very dangerous if you're not somehow adjusting for that non-stationarity, because it can make bad decisions at the beginning. So yeah, that's, sorry, long comment and long question, but very interesting work.
Thanks. And I think that's so helpful thinking about the trade-off between regret and your inference. I do think it's harder when you come to contextual policies. I've found that in practice, those are really hard to evaluate on adaptively collected data, and to get estimates, to get inference that would be comparable to even what you would get if you had just randomly collected data. That you're often better off just, if you know what your policy is that you want to evaluate, you are often better off just using randomly collected data, completely randomly, as compared to adaptively collected data. Even if that adaptive algorithm is going for the same thing that your policy is going for, there are enough problems with the imbalance in treatment assignment probabilities. But I think that's great, and I think that's useful feedback for me too for presenting this going forward. In terms of the non-stationarity, so the algorithm that we're using that I presented here is not batch-wise. We're doing online updating after a meaningful first batch. And in practice, we're getting 1,500 or 2,000 observations per concern category for our learning, where we're just trying to learn which message is best. Non-stationarity is really a problem. It's really a problem in these settings on Facebook. I haven't addressed it here in this talk, but it's absolutely a problem when you don't have control over your sample. That it might be that people who are coming into your experiment later fundamentally look different than people who are coming to your experiment early on. So I have elided that, and now you are exposing that I have elided that. I have not addressed it. What we do try to do is get enough batches or get enough data that we have we think that we're pretty confident that we're getting something that is overall going to perform well, and we're not getting something that will be just kind of pretty noisy early on. And then we do our evaluation very soon after. So we are trying to get an evaluation phase that's very, very close to our learning phase so that there's not that much temporal difference. I haven't been using algorithms that adjust for that, that type of instability. I know that there are. And I think if we were running longer adaptive experiments, or we were more concerned about getting even more diverse samples, we'd account for that. But that is a really meaningful consideration. But what I basically said is we're hoping that it's not big enough of a problem in our actual application. But I really appreciate that concern. Yeah.
This is a question for Alison. Thank you for the talk. These kids always give me a headache in terms of trying to figure out what they're doing. I wonder whether you could say a little bit more about why you think the children are exploring a bigger hypothesis space than the adults. So in particular, what I'm wondering is that to what extent are they actively or consciously exploring this larger hypothesis space, as opposed to just doing all sorts of things and collecting all sorts of different data, and then in the end backing out an explanation of that fits the phenomena retrospectively?
Yeah, I mean, I think this is, for me, this is like the big interesting question that's going to be the focus of both the AI and the developmental work, which is, again, I think that's this question about how much is random exploration and how much is some kind of directed exploration. And we know it's not completely random in all of these cases. And in some cases, there's a paper that just came out with Eric Schultz and Azura Ruggieri, where, you know, in like a simple RL bandit task, you can specify whether things are to what extent things are random and to what extent things are directed. And what they found is that the younger kids do more random exploration. Now that's where you're actually, you know, looking at the policies they have, not what's going on internally in their hypothesis sampling. And what they find is that the kids are doing both more random and more directed exploration than the adults are. But there does seem to be this developmental sequence where you start out more random and then move towards things that are more directed, but you're never completely random. You're always doing things that are at least partly directed. And I think it's a really interesting question about what kind of balance and how you would achieve the balance at a higher level between doing a kind of random exploration and doing a more directed exploration, both when you're trying to explore the hypothesis space and when you're trying to do exploratory policies, where you're actually trying to design interventions. I mean, in that Blicket detector case, I think one thing that's clear is it's not that the kids are just, in fact, we compared them against a random algorithm, and they're clearly not doing things that are just random. They're adapting depending on what the actual structure is. So they are performing different interventions when the actual structure is conjunctive versus disjunctive. And they're doing different things when they get the hypothesis space and when they don't get the hypothesis space. But exactly what it is that they're doing, that was partly why I was thinking if people have some ideas about that, that's still sort of up for grabs. One last thing to say, going back to one of the slides that I showed you, when we did that study where we looked at the whole age range from preschoolers to grown-ups, one possibility is that it's not so much that the kids are searching more broadly, it's just that they have a less peaked prior, they have a flatter prior. And that's an obvious possibility, and it's probably partly true. So they just don't have as much evidence for one over hypothesis versus another one, which in itself is interesting, and that would lead them to search more broadly. But it's kind of interesting. If that was true, you'd sort of think that there would just be a linear relationship between how old you were and how likely you were to have the narrower, more peaked prior, because presumably you're getting information on a fairly regular basis. And instead what we found was there are these big shifts from preschool to school age and then from school age to adolescence, which suggests that, and we know that there are like differences, big neural shifts at those points, which suggests that there might be something sort of more intrinsically different about how the searching's going on. I don't know if I think that was answering your question, or at least relevant to answering your question.
Hi, it's also for Alison. It's kind of related to the previous question. So you mentioned, and I think here as well, that one of the advantages that children might have in exploring these spaces that they take these larger moves. So essentially they explore that space a lot more widely, perhaps, than adults would. And you mentioned that also that might be an indication that in AI methods, perhaps we need to be moving bigger moves, bigger proposals, make a step a little bit further from our data when we are exploring the space. And I'm not working in that field, but it made me think about self-driving cars and how I'm imagining self-driving cars trying to make decisions that are not, that they're trying to explore optimal ways to drive around, not solely based on data, but also based on some form of intuition that perhaps like similar to what children have. So, and then ethical problems come into play about how we're exploring the space widely outside of the information that we have been receiving. And I just wanted to like understand what, if you see any problems in that, imagine like a child, perhaps if you don't like close the outlets, they'll put their finger in there because it's dangerous, but there's a little bit of a control environment there. So how are you imagining like us controlling AI at the same time as letting it explore these spaces better?
Yeah, I mean, I think that's a really good question. And I think, again, the evolutionary design of development is an interesting kind of model. So we actually disable, I mean, this is going to sound funny, but like we disable our explorers by having them be children who are weak and can't do very much. You wouldn't think about, why is it that 2-year-olds can't take care of themselves, right? I mean, it would obviously be better. Why are they little? Why don't they have very good executive function? Why aren't they very good at planning? All of those things would seem like problems. And part of what I've suggested is that might actually help them in exploring. But another thing that it might do is keep them from really negative outcomes, right? So if you can't do as much, then ironically, what that means is that you can explore without necessarily having to deal with the outcomes. And then, of course, the other thing is that that's the last part of my point about social learning, is that you have grown-ups and adults who are designed to actually be the ones who enable this to be a context in which you can explore. And then a last one that I think is really interesting is kids spend a lot of time playing and specifically pretending. And one of the great puzzles in psychology has always been, why would you spend so much time thinking about things that are not true and are far removed from any of the real things that you're going to have to deal with? And one thought is you could think of that as being the equivalent of, say, using your self-driving cars in simulation. We've done some of that at Berkeley for a long time before you actually let them go out into the world. So you might want to think if you could explore in the simulated environment the way that kids are doing when they're pretending, for example, then you don't have to worry as much about some of those ethical and practical consequences. And we actually have a very nice project that we're doing with some of the people at Google Brain, where in robotics, for example, actually letting the robot, instead of the robots imitating the intentional actions of people, having them imitate play, having them actually be trained with data that comes from play, actually means that when the robots are implementing things, they're more robust. So even though the play isn't actually bringing about the outcomes that you want, that actually seems to be a better way of training. And we're doing that now with using some of these VR environments with kids actually being able to just explore a space and then see what giving that information to a robot agent does.
Hi, Molly. Very interesting talk. So I have 2 questions. My first question is like, for your online algorithm, when you just make the decision of what policy we should use at the next time point, are you make the decision based on the counterfactual outcome at the current time point, based on the recent past, or are you just making the decision based on some estimated conditional mean outcome regressions? The second question is like, it seems to me like the algorithm itself doesn't provide how should we choose among different adaptive design strategies. So suppose I have two adaptive design strategies. Is there any way that I can choose between them when I see more and more data coming? Yeah, that is my question.
Okay, so let me see if I understand your first question, which is, if I rephrase it, when we do our evaluation phase, how are we doing our policy learning for the policy that we're evaluating? Do we just use unadjusted estimates, or do we use some kind of doubly robust estimates where we adjust for covariance? Is that the question?
I mean, like, do you make the decision based on some counterfactuals? Do you still use the causal inference framework in that step, or do you simply use the observed data?
I'm not sure if I quite understand. I mean, we are estimating what response would be across our distribution under each of the different versions of treatment. So in that sense, yes, we're thinking about counterfactuals. We're thinking about what response would be under each of the different versions of treatment.
Okay, got you.
Okay, and the other question was, sorry, how do we compare algorithms and decide which one is best for us? If we have potentially two algorithms that have the same objective, that have the same optimization procedure. I mean, I don't have a good decision rule for that. I would love if people are working on that or have thoughts on that. The way that I would approach this would be basically to apply this in simulations to the settings that I think I'm going to be operating in and see how they perform in finite samples, because a lot of what we know about these algorithms is asymptotic. But I would love if people have better approaches to a decision rule that you could give to practitioners and say, you know, consider these two alternatives, and here's a good approach to doing that. That's more structured than just trying it out and seeing what works.
I have one question for Alison and one for Avi. We'll take them separately. So in the exploit trade-off, that, I mean, it depends on the time horizon, right? So how long we can exploit. So a possible explanation for what you observe could be that adults realize that this is a very specific environment, and learning to differentiate the rule between stripes and dots will not carry any utility outside of this very limited lab experiment, right? So have you looked at altering the time horizon factor and seeing if that can explain the differences between children and adults?
Yeah, so one of the questions is, one of the arguments that people have made is part of the reason why you might see this is exactly because the time horizon the reason why you might see the early explore and then the later exploit is exactly because the time horizons by definition are different. So by definition, you're going to have a longer time horizon early on in the process than you are later in the process. With the learning trap, those particular approach avoid experiments, I'm not sure that actually expanding the temporal window is going to help, because what happens is that once you start committing to the particular policy about the avoiding, then all the data that you're getting is confirming what your original hypothesis was. Now, it could be that if we just gave them a somewhat longer, I mean, it is true in general that with longer time horizons, you see more exploration. But I think what Gorekis and Todd found, and, you know, again, if you think about some of these examples in real life, like anxiety disorders or phobias, even when there's quite a long time horizon, you know, even when you think that your decisions about getting on airplanes are going to be relevant for many, many decisions over a long time, you can get stuck in this local minimum of avoidance. So I think it is true that the time horizon might change things, but I think what Gorekis et al. Found is that even when you give people a longer time horizon in this kind of approach avoid context, they still get stuck in the local minimum. And, you know, phenomenologically, when adults are doing this, their affect is, oh, this is great. I figured this out. I figured out what the hypothesis is. All the data I'm getting is completely consistent with that. So I'm doing brilliantly, and I'm just gonna keep going.
That makes sense. Yeah.
By the way, there's a beautiful result that I love. It's one of my favorite neuroscience results. When they were looking at these explore-exploit, Beckett-Ebitz looked at these explore-exploit decisions in primates where you could actually measure brain activity. And what they found was that the decision-making parts of the brain at the time when you were doing the explore choice. So, then you can very carefully say, is the animal doing the explore choice or doing the explode choice? And they thought that what might be happening is that you'd see a distinctive pattern in decision-making parts of the brain. In fact, what they found is that there was this injection of noise into the decision-making parts of the brain. So it was as if what the brain was doing was not saying, okay, I better start exploring now because then I'll get more information that might do me more good in the long run. It was more like what the brain was saying was, oh, the hell with this. This is boring. I'm bored. I just want to go and try something. I'm just going to do something else randomly. And that seemed like that was kind of more the situation. But I think it's a very, very interesting question.
Thank you. So Avi, we have talked about this before, but I'm interested in your updated view on it. So these treatment probabilities in the end of your talk, like in many of these settings, it doesn't really make sense talking about treatment probabilities. So should we see them, like conceptually should we see them as representing something, or should we see them as more of a tool of balancing? If so, what do the kind of weights, the treatment assignment probability perspective change just or bring to the table compared to just looking at the raw synthetic control weights?
Yeah, so no, thanks for that question, Frederick. It's as you said, it's something we've talked about many times over the years, and this is something where I think the kind of canonical synthetic control setting really can lead to these pathological settings. So what does it mean to talk about the probability of West Germany reunifying, right, as a propensity score? And it's not really clear. Like, it's not also clear we would even define that counterfactual for one of these other countries. What does it make sense to say Austria reunifying with West Germany? Like, that's with East Germany, right? That's some of these counterfactuals just don't even make sense. So there's definitely these corner cases, and you start entering into these kind of theological questions there. Lots of different ways to answer your question more broadly, right? I think there are certainly corner cases where I'm never going to come up with a good answer. The question is, okay, how is this perspective useful? And I think for me, it's useful in that we're not always in that one treated unit setting, right? So in the case of states adopting a new policy, right? We can actually imagine these as valid treatment probabilities. And I think for me, in terms of how to categorize methods, it's very helpful for me to put this side by side with, say, more traditional IPW in a lot of those settings. So, I think the first part of my answer is, when I'm not in a corner case, right, this connection to estimating these probability of treatment assignment weights allows me to compare synth, for example, to other methods that get at those same kinds of weights, like traditional IPW. So that's one way to just kind of do apples to apples. I think the other part of this that is hard is, so we have a new paper, I don't think David's here. We have a new paper coming out at AI Stats that looks at the role of these true propensities, right? Or in ML, we sometimes we'll call this like the density ratio that you're trying to estimate directly. And one of the things we're finding is that actually in settings like synthetic controls or other balancing weights problems, we kind of have this implicit outcome model. It's actually the line between like a pure design-based approach and outcome modeling is somewhat blurred. And so it's not a satisfying answer to your question, but I think it's in a lot of these cases where there's really just one treated unit, we can't necessarily conceptualize this probability of treatment. We can sometimes start to think about these balancing weight style approaches as actually approximating something in an outcome model or class of outcome models. And so again, I'm not taking that treatment assignment that probability seriously. I'm thinking that as a tool to get at an estimation approach. But it's tough. I will say the one thing that we've talked about a lot that I disagree with some others on is that a common inference approach in synthetic controls is to do a uniform permutation across units, and setting aside these corner cases, right, where we don't really know how to reason about the probability of treatment. In settings where we do think that that's a well-defined probability, then a uniform permutation is somewhat at odds with that with that weighted, with this probability of treatment. And so maybe that's a good idea, maybe it's a bad idea, maybe the way you justify it is different, but it does mean that they're kind of getting at different questions there. So it's a rambling answer because it's a big hard problem. Sounds like maybe Angela and I need to discuss it more later.
Thank you all so much. And thank you to all the three speakers for really wonderful talks. Let's give them all another. So this afternoon is for continuing these kinds of discussions.